You get weird code if you code with painkillers.
Is it what?
I said if you're on painkillers from the dentist, you get weird code.
Oh, yeah, I learned the whole coding while on drugs when I was in my 20s. Possibly when those fillings went in, actually, now that you've said that. And
Yeah,
I don't make that mistake anymore.
alcohol is another drug that I remember using back in university. We'd go to the bar at midnight when the mainframe would tell us the time change and close the place and then go back to work.
Yes. And then how was your code in the morning?
It's great.
Wow. Mine was always a case of, wow, that was weird. What was I trying to do here? And then a little bit later, that's broken. Oh, that's broken. This is all broken. What was I thinking? And then just, unwind. Try again. All right, let me do the intro here. So this is Coffee Compiler Club. I promise I'll get the video out. I know I have like stacked 2 videos I need to get after, so I've been fighting medical issues. But here today to talk about compilers, language runtimes, garbage collection, concurrency, typing systems, anything and everything to do with compilers and languages. And it's all been recorded, and I claim I'll put it up on YouTube at some point in the future. Open mic, say what you want. Mute if you're not talking. I reserve right to moderate. Never had to do it. It's all good. So with that, my progress report is my dental work sucked, and I did a lot of tech debt elimination cleanup and more consulting gigs and had no language progress report other than tech debt elimination. It was like a grind. Anyone else want to go?
Well, that was quick.
Yeah, there you go. I know. So Cameron, when you hold your hands like this and you have a little bit of green flash on your shirt, it looks like you're knitting something you've got tucked under your arm.
Yeah, I've got
Oh,
a
you
mic.
don't have your cast on.
Right.
Ah, nice. How's it going? See, speaking of medical issues, this is like old fart medical day.
You know, some discomfort, but good. I've been
Excellent.
skiing and snowboard. I'm snowboarding now, so.
It's going to break the other arm now, or is it the ankles? I forget which one. Snowboarding.
Hopefully nothing.
Hopefully none of the above. Yes, hopefully none of the above. Bye.
I have a topic, if nobody else has something.
Yeah.
Dynamic dispatch. Here we go. Because I've been looking into this lately. Because for the context, in my language, you have classes, you have interfaces. Interfaces can be implemented in any particular order. And they're implemented after the class is defined. And so originally I was looking towards fat pointers because it gives a couple of benefits in terms of performance with lookups. And a nice added benefit is that new types become quite easy to implement because you can just use fat pointers for them. But then I realized that downcasting a concrete type to an interface type comes with a runtime cost, especially if it's inside a other type. So if you have, say, an array of integers, and you want to cast that to an array of 2 string interfaces, that would require duplicating the array. And then, for the values, you have to load the v table, assign it to the fat pointers, etc. And so I've taken a detour there to see if there's alternatives to that. Also because, fat pointers have twice the space compared to a normal one. And I came across this interesting approach. I'll link the article in a second, where somebody basically concluded the same, and they went down this path of, I think it's best described as a sort of restricted subset of perfect hashing, by doing it at compile time.
I threw out what Hotspot does as a link.
Right. And so basically what they do here is they, for dynamic dispatch, they do hashing, but the hashes are calculated at compile time. And there's a couple of other tricks to avoid using the typical modulo operator. And then I started looking into that in things like, perfect hashing, minimal perfect hashing, etc. And I'm kind of curious what the experiences have been of the people here with perhaps the less commonly used ones. Because I know Java, they have invoke interface, which involves a linear scan through the list of tables with some caching.
Yeah.
And then C# has something similar, but they have what are they calling it? Like method slots. They have some extra indirection, so they can patch stuff more easily. And then, well, they have C++, how they do it, and then it's basically fat pointers with Rust. It seems this hashing approach. I found a couple of papers from like the early 2000s that discuss it.
Are you expecting to see lots of interface calls as opposed to lots of classic virtual calls?
So in my case, yes, and that's because for my generics, I don't do monomorphizing.
Okay.
One, because I never really implemented it, and two, because I do support generic closures, and I'm not sure how you monomorphize those.
Yeah.
And even if you could, there are some downsides for having lots of different implementations of more or less the same method. Because right now, at least my runtime wouldn't really take advantage of it. And so
monomorphize, or you need a tree structure to the types, right?
Sorry,
I'm missing. Maybe we're not using.
Oh, right. So yes, there's going to be quite a few interface calls, and that is because I don't monomorphize my code, and so a lot of generic code will actually have to do an interface call.
Okay, as opposed to
right,
okay.
Opposed to concrete, and I don't have inlining yet and all that, so basically I'm at this state where it's sort of the worst possible scenario.
Right. Yeah.
But
right.
even with all the optimizations, there may be cases where you need to do a interface call.
Yeah. Yep.
So I'm kind of curious what the sort of opinions are on this, because this hashing approach looks quite interesting. It, in particular, doesn't seem to suffer from the usual problems of perfect hashing, that being that it can take forever to find the appropriate hash functions, or it takes a lot of memory, or it's not very fast to run. So there's usually some trade-off.
I haven't seen this one then.
If all you need is no collisions from a small space, you can just multiply by a random number, move from high, and then mask off the low bits of that, and just keep picking random numbers till you find one that happens to work.
Yeah. So what this article talks about, they excuse me, they talk about hashing.
Yeah, if you have perfect hashing, you get to cheat on the lookup over a hash table. That's the trick. So you must have a perfect, no, not even a nearly perfect.
Yeah, because the approach I've been experimenting with is I'm not even hashing functions, because I started with that. I just used f&v as a start. And then I realized, like, hey, in my approach, every unique name has a unique hash. But so if you have two methods with the same name, they have the same hash. And that's okay, because you can't define the same method, two different methods with the same name on the same type anyway. And then I realized, hey, if every name has a unique hash, why not just give them an incrementing integer? So I'm not even hashing. But it's the approach I'm taking, similar to this article, is to use linear probing for the collision case, which I think works fine. It's easy to implement, it's pretty fast.
Yeah,
you can do this.
I do linear probing in my hash tables, or I've certainly messed around with it. Typically works well.
Yeah, like linear probing, as far as I know, it's fine.
The issue with linear probing in a hash table for a function call is it's not a perfect hash. So you have to have a test, retry, scan loop, and that's just your scan loop that Hotspot does. Imagine your hash function sucked. now you're in a linear scan anyhow.
Right, and so this essentially what this article does, the length of the function table is a power of 2.
Yeah.
Which I expected it to waste quite a bit of space, but I took a quick look at least the classes that I have now, and it's actually not that bad.
Right. Non-blocking hash map is a power of 2 size table that does linear probing.
Right. The issue is you can still have collisions. Different hashes go in the same bucket, and that seems to happen often enough that you need to make sure that
if
the
your power
probing is fast enough.
Don't have buckets.
Yeah, buckets. I mean the offsets where you put the functions basically.
Flat array, and you're essentially you hash to the first spot, and then you linear probe till you get your
exactly.
Yeah.
So the interesting thing,
a better starting point.
I thought you could do there is if you have multiple functions that are hashed to the same offset, basically, you could at compile time order them in frequency from more frequently called to less frequently called. And you still need a cache on top, and I think in my case probably a polymorphic inline cache.
So I did a bunch of this stuff at Hotspot, not the hashing, but the PIC stuff. And polymorphic inline caches beyond 1 pay off only rarely in very specialized circumstances. Literally the 1 covers, like until you get into alternative languages that are using interfaces at every call site, which you're in. But if you look at the Java code as people write Java code as opposed to Groovy on Java, the 1 element cache does 99% of your hits. The 2 and the 3 guys cover a handful of very specific cases that are hot and nothing else. So literally, like every Java program, average across every Java program on the planet, much less than 1% gain to going polymorphic. And then the next piece of that is it becomes much more difficult to do concurrent updates to the polymorphic inline cache, racy concurrent updates. You basically kill the cache while you're doing the update. It's fine.
Yeah, because that's my this hashing approach seems reasonable. There's a couple of papers that do similar stuff. I had some trouble following them along because they basically throw formulas at you right away, and then I get lost in that. It's more like, okay, you need some sort of caching fallback for this, and I think that's where things get a bit hairy. And I think that's what initially drew me to thap pointers, because you can use those without caching, basically. I'm kind of curious, since I would expect most people in here to have a lot more experience than I do with this. Just curious.
Well, you think you're going to have a lot of interfaces. I don't know. It sounds like you're on the right track. I would do a 1 element cache, and if that fails, fall back to a linear scan with a power of 2 size table with a better starting point, which is a hash, but now you're in a linear scan mode. If you can get a perfect hash, you can skip the scan. Perfect hash. The issue is you have to emit code. So for Hotspot, that search down the linear scan, that's what we would call millicode, handwritten machine code that was custom tailored to every backend target, but it never entered what we call entered the runtime. You didn't change execution states from running in JIT'ed managed code to running in your underlying C implementation code. You just jumped to machine code that walked the table and produced the answer. And if it fell off the end, that was a death call that, you get a bug in your VM. So, then you jumped away, and what Flavio was running into was that if you do it all the time and you have 20 things to search through, your linear scan of 20, it's not great. It makes a function call take 20 odd clocks, or however many, 1 clock per test. If it's linear, if it's truly linear, it's 1 clock per test. Still 20 adds up. If you do a hash and probe and you jump in and you mask with a round off for power of 2, you add a round off per probe miss, you're still linear scanning, and you do your first touch math, which is more complicated than just going to the base of the table. But that comes back to you if you're typically scanning 20 entries anyhow, and now you're going to scan 3 instead of 20 on average, or 2 or something. So, you know, maybe I think you'd rather not be doing interface calls, seriously, in the big picture way. But if you have to do them, then I don't know. That sounds good to me. But do the 1 entry cache.
Mm-hmm. Yeah, and I mean, long term, of course, you would want to optimize away as many interface calls as you can.
Well,
I said long-term.
Well, I'm implying something different. You want to arrange yourself that you can use a direct call mechanism like a vtable.
Right. I mean, for static calls, that's basically what I will be doing. Vtable in the class, and the hashing basically resolves to the offsets for that. I think probably, you know, with inlining, devirtualization, etc., you can probably get rid of most of it. But that's, at least for my compiler, probably a few years from now.
Yeah.
Yeah.
Hotspot got rid of a fair amount, but as soon as you went to these alternative dispatch language types, the JIT optimizer didn't understand the semantics, and so it did not clean any of it out. You know, if you're doing Java code or Java bytecodes and you have virtual calls and interface calls, many of them go away. Something like 90% go away, become static. As soon as you're doing JRuby, Jython, Groovy calls, none of them go away. You know, I don't know if that's a failure in the JIT or it's a failure in the translation step or whatever. I went with a lot of these, like Charlie Gracie's not here, but I helped him for some years ago to sort of step through how to generate code that at least an inline cache could cache, but also how to generate code to give a help to the compiler. His problem was at the point at which the compiler could understand the virtual call that you were targeting was hidden in a shared piece of code that was just a little bit complicated. And as soon as the JIT decided it was highly shared and a little complicated, he just made everyone call the piece. And then all call smarts got approximated when 200,000 people called the same function. And it needed to be inlined at every call site. And it wasn't too big, but it was bigger than what the JIT would typically have inlined all the time. It would inline it periodically, but not everywhere. And you had to go do something to teach the JIT. You must inline this or I suck. Which in my case, I think what I told Charlie to do was make the piece that's the fast path that's going to work as tiny as possible and have a separate function body for the complicated lookup step when you failed. And that let the JIT inline sort of for free. Vtables, I think I know. And then caching shenanigans. What is this one? Interface. Oh,
Yeah,
interface.
no, maybe related to that. Are there, or are any of you familiar with like any optimizations for the case of fat pointers where you want to downcast? Because as far as I know, they're assuming you truly have a case where optimizations can't get rid of it, and you have to downcast, say, an array of ints to an array of some sort of interface.
Hotspot has a subtyping test that works arrays and objects and types in all directions. And
yeah, so I can see there being the optimization where you say, okay, we're casting to an array. What we'll do is we'll look up the target vtable once instead of for every value, and then just assign it to the new pointers. But you still need to create that new array.
I'm sorry.
Yeah,
if I'm handed an array of object and somebody wants to genericize, pull out strings out of it, and I'm endlessly, you're talking about this kind of case where you hand an array of objects.
Imagine a function where you have some variable, it's an array of, let's say something a bit more complex than numbers, an array of users, whatever. And pass it to some function that, let's say an array of admin users, and you pass it to a function that expects an array of users, where a user is an interface. Specifically, I'm using not integers here because you can maybe cheat there by copying and stuff like that because it's cheap. But in other words, your input is quite expensive to copy.
Right. So
especially
we
if
certainly
this-
don't ever copy these things because that's sort of a no-brainer for performance.
Right.
Talking about whether or not you upcast every element once or every time. You don't have sharpness in your array in what you're describing. So every element that comes out of that array could be a user or it could be a cat, dog, frog. And so
Right.
there you have to test everybody who pulls out of the array. Now you have to test everybody.
Oh, right, yeah.
I have optimizations for where I'm handed an array of some loose type and I'm typed it as a loose and I'm going to sharpen it. I have the store version where I'm going to have an array of object I'm storing, but it's actually an array of whatever sharper, and you want to cast all your inputs to the sharper type as you go and whatever. There's a bunch of optimizations to do where you're handed a loose type for the array. It's in practice a sharp type. Can I do something about it? So if I'm handing an array of object that's a generic top level type, but it's actually typed as an array of user. Then there's a version which says I check for it's an array of user. It is. I now know that everything's a user. I pull it out without typing further. Is that the case? That one Hotspot does. Which begs the question, what do you do if it's not an array of user and that's just a deopt and try again?
Yeah, but you made a good point that you basically do the cast when you fetch values from it, not when you pass them.
Yeah.
Because then you don't have to duplicate anything. Basically, just when you load it.
Yeah, no, never duplicate the array. But when you load it,
yeah, and then you say, oh, wait, we want this v table
and
instead.
the one entry cache for subtyping check will win every time here because they're all in fact user types. So you'll cache a user in there and you'll pull them out, see it's a user, and you got it.
Yeah, I'm kind of curious there if you could get away with not caching, as in you pull a value out of the array and you say, screw whatever the v table is. We know it's going to be this, so we just create a new fat pointer with that v table. If it's already the same v table, that is a bit of a waste, but I'm not sure if that's more wasteful than checking if it's the same v table and then deciding, oh, it is, so we don't need sorry, it isn't, so we still have to do the work.
If you let your user cache to something that's a different size, you're going to get a security bug where things start running over into other memory, right?
Well, it's a different type. Doesn't matter if it's size or not. It's just different type. You must test here. Yes, you must have a runtime test for security bug. And in fact, for about a decade, I had a short 5-10 line Java program that demonstrated the security bug by doing, the bytecodes were all correct, but the runtime failed to put the correct type check in and around array loads. And I could just declare anything as an anything else and promptly walk through all your security. So I'm not doing anything with fat pointers, but if I pull out a thing from an array that originally I wasn't told what type it is, but in fact, and then I'm all going to cast it to user. If I look and see that the array is array of user, I don't have to further check anything else. They're just users, and the compiler knows it's a user, so there's no fat pointer generation. The compiler just knows it's user, and we're done here. And that's an optimization Hotspot does, where he recognizes you are endlessly casting to a fixed known type when you pull out of an array and you're looping on an array, and I test the array body up front, and then generate the code. And that test is done with profiling. It's a heroic optimization done with profiling. It happens to be an array of user this go around. So there's a bailout path if you ever hand me an array of something else. But I test it once, and then forevermore, it's array of user. You're only pulling users out, no more test in the body of the loop.
Yeah, no, those are good points. I think the mentioned about security, I'm not sure if that's an issue for me because all my data currently goes on a heap anyway. So the inputs are all pointers. There's no no inline values or anything like that. One concern there is I think when you explicitly cast a type, so you have again, let's say your array of admins, whatever, and you explicitly cast that to a array of users. I think at that point you probably do want to convert things as part of that cast.
Okay,
Otherwise,
so we're talking different terms here. If I'm handed an array that's typed only, compiler only knows it as an array of object, the runtime knows it as an array of user. Nothing more than a typical one clock test will come tell me the entire array is array of user, and then I only ever pull users out.
all right. But so let's say
It's assuming there's such a type as array of user. I mean, it's assuming a reification of generics.
Yeah, I'm proposing it looks like a generics kind of thing, although people would write this long before generics. I'm trying to get York's use case figured out.
right. Yeah. So maybe the use case perhaps better. Let me see if I can quickly think of a case. There are some cases, if I remember correctly, where in my type checker, I traverse the AST, and then I have some sort of concrete AST node. And in this case, I usually want to pass it to a function that takes an interface. So that's that first case that we had. But I would imagine there's a case where you have a concrete type. You want to explicitly cast it to a interface, or perhaps a concrete type containing an interface.
So when you say you have a concrete type, you're talking about an array of them, or just a concrete type? I have a person or whatever.
Let's say perhaps more complex. Your outer type is, let's say, a let me quickly think. Some structure, whatever the type is, and it has a bunch of fields, and they're as input they're all concrete types, and you want to cast that surrounding type. Say it's a generic type foo with that's initialized to parameters thing, whatever, and you want to cast that to a foo with the parameter being a bar, which is an interface. What happens, the outer type basically stays the same, but some of its fields would then have to be turned from a concrete type into an interface. And in the case of fat pointers, that means switching the v tables.
Okay. Yeah, in the land of Java, we would just know that it was a concrete type that either did or did not know that it directly implemented an interface, and didn't. We have to do a subtype check every time when you loaded the field.
Oh, right. So basically, whenever you have an array of interfaces, you would do a check like, hey, is this actually that interface, or is it some type we first have to cast to that interface?
Yes. So we do class hierarchy analysis. Sometimes a class hierarchy analysis will tell you that this thing must implement the interface, but sometimes it only tells you it may implement the interface. And if you get the may version of it, you have to do a runtime check. And then the runtime check typically comes back to you in the language level. Somebody has to cast it. And then at the casting point, that's where you do the runtime check. And then the JIT moves the runtime check around according to where he cares to, where it makes sense for performance and commonality. You can hoist them and you can sync them to their first security safe spot and blah, blah, blah. He moves them around, but there's a runtime check. Specifically in the case of arrays, where you're looping over this runtime check, we also check that the array itself already is of a concrete type, which must implement the interface. And then we can skip the looped version, the test in the body of the loop. And that test can fail, and it's correct both ways, and you see it commonly happen both ways. So we do the little profile hack where we say, at the time the JIT was kicked off, what is the actual concrete type from the interpreter stack frame? And is it of the right type? Okay, we'll try the optimistic thing, and we put but if it's the wrong kind, we have to test every time in the by loop. We'll JIT the test, you know, in the loop. If you got some other kind of complicated object, not an array, we don't do that. So if you're just pulling fields out and the field is concrete, but it only may implement the interface, we put the runtime check in.
All right, yeah, because I think Rust takes an interesting approach there where they just straight up don't allow it. They have some simple case. If you have like a vector of something and you pass it directly to a function argument that expects a vector of some interface, it will handle that for you. But if you first assign
When you
that
say
vector
handle it for you,
they sort of cast it for you, basically. So
they do the runtime check.
no. So they do it at compile time through their inference. So basically, when you pass a vector of values directly,
Yeah,
it knows, oh, we are passing, you know, a vector of ints to something that expects a vector of some interface. Oh, so then we'll just assume, or basically turn that vector already into that.
that only works if you must implement that interface.
Yeah. So they don't allow you to, you know, cast it willy-nilly to anything.
Okay.
And they have some limitation. I think if you were to assign that vector to a variable first, and then you explicitly annotate it as, hey, this is a vector of integers, and then you pass it, then the compiler is like, and I think that works for Rust because interface calls are quite rare in Rust.
But they were rare in Java too until, I don't know, people started using all kind of funny languages on it. So I'm just, warning for the Rust folks, don't assume they're going to be rare forever.
No, and that's
Right.
I kind of, in a way, I like that idea because explicit casts aren't that common, at least so far in my code, and I generally find there's better ways of dealing with that, say pattern matching.
Explicit casts are pain for the user to write.
Yeah.
So people don't want to write them, so they'll look for a way around. Yeah.
Right, and so I'm still a bit on the fence where I'm thinking, hold on, where I'm thinking, hey, maybe when you do a cast and you have, say, an outer concrete type with something in it, and you want to cast it to an outer concrete type with an interface in it, to just disallow that and say, hey, you first have to cast that inner thing yourself and then sort of work your way outwards. Because then at runtime,
demands the cast at the bytecode level on the inner thing.
Right.
Yeah.
Because then you can do these things like, oh, then we'll just generate some code so that at runtime, you know, flips the vtables. And because it's inside out, you don't have to copy anything because you sort of, quote unquote, let the user copy it.
Well, no copy. Oh, and hotspot is no copy because there's no fat pointer. You're saying you want
it's not really a copy, I guess. It might
constructing a new header in a sense.
Yeah.
Yeah, right. And hotspot doesn't do that. It just declares that you implement the interface because he sharpens your type to the concrete type, which must implement the interface from whatever concrete type you started with. And now that concrete type moves forward. Like the virtual machine only ever has concrete types. The interfaces are strictly used for allowing calls to be made, but there's no such thing as a concrete interface type.
Yeah, and this is where all those things come in about, you know, covariant, contravariant, invariant.
Yeah.
And you know, from a language designer's point of view, I'm sorry, from a computer scientist's point of view, everything should be invariant.
Okay, fine.
And from a language designer's point of view, everything should be covariant.
Yeah.
Because so I've had this argument with a guy you might know, who thinks that Java's array covariance is a bug.
Yes.
Right? And say, well, no, the bytecode might be poorly designed for it because it's not optimizable, but the concept itself is quite nice, right? Because I don't want to have to write a copy for an array of animal versus a copy for an array of object versus a copy for an array of string, right? So I want to be able to write a method called copy that takes an array.
Yeah, it's fairly optimizable.
Right, but where it gets non-optimizable is when reading and or writing to it. So take the cat animal example, right?
Yeah.
So I have a function that takes an array of animals and it puts a dog into cell 3.
Yeah.
And I pass it an array of cats because an array of cats is an array of animals, but array of cats is not an array of dogs.
Yeah.
Okay? So there has to be a runtime check. And because of it, the code is always produced to do the runtime check.
Yes. And also
And it doesn't have to be.
There's a lot of confusion about when, from a user's point of view, about I have an array of object or an array of string. And so I can put objects in, or I can put strings in, or I can't put strings in, and the array of ints versus objects versus whatever. I don't have a better way to think about the problem, but it does feel like it's clunkier than hell.
Covariance, you mean, or?
Yeah. Oh, array covariance. Thinking about array covariance.
Yeah, I never think about it. It's just the way Java did it is very natural. It just works. Like
Well,
I've never tried to put a dog in an array of cats. Ever.
up until it doesn't. Oh, I've seen people do it all the time. I guess I see all the bad cases because it's the JIT coming around, but you get all the bad cases all the time. People will attempt, they'll get a complicated hierarchy, and then they'll pass an array of something further down the hierarchy into some other place, which is generically taking an array of objects, and then they're all confused why they can't store, and then they figure it out, but they don't know what to deal with it. So I'm saying it's a confusion about how to deal with it. Like there's another version which says the array has no type other than garbage collected pointer, but I don't, that kind of sucks too. So I don't know what the right answer is. Fine. So I'll shut up now. I don't have an answer, so I'll shut up.
I think to Yorick's, what Yorick was suggesting or trying to describe. So we have a kind of a concept of, if you will, a view type, the type that you're viewing something as. So, if your function takes an array of animal, then your view type within that function is an array of animal. And you could pass a more narrow type into it because of covariance. But when you do that, and this is what York meant about creating a new fat pointer, when you do that, you have to put preambles in front of some of your, at the fronts of your method chain. So for example, a virtual store into the array now has to do a cast. When I say cast, it's a bad word. Cast is a silly word. You have to do a type assertion.
Yeah.
So you add a preamble, and then the V table, instead of going directly to the array of cat store, it goes to the array of animal store, which does an assertion, type assertion for cat, and then supers, if you will. It's all obviously in line, but conceptually supers to the array of cat store.
The Java array stores aren't virtual, so the JIT gets the
right. But Java, the same is true for the collections as well. So that's why C# dramatically is faster for these types of examples because of the reification. So they can detect this. They can also do the boxing avoidance. So those are the two places where C# has an advantage performance-wise.
I'd have to go see that. I see what they did, because certainly if you do an array store, there's an array store check, which is just what you're talking about. There's a type assertion right there. But if it's in a loop because it's an array,
so the reason why C# is better for this particular one, and I'm going back years in my memory to
that's fine.
stuff I looked at, but when I pass, so Java always checks to make sure it's
the semantics are that Java always checks.
Right.
Implementation shortcuts the hell out of our loops.
Right. You may be able to raise that out of
Yeah, you typically do raise it out of the loop. I mean, that's what I was just talking about with Yorick, that there's a There's a check made up front at the time I'm JIT'ing that the reason I came here to get JITted was because some interpreter ran an array store. I look at the type that was there. If that was a compatible version, then I'll JIT a test for the sharper type on the spot with a bailout path that says, give it up, try again the hard way, where you have to test every time. But if you're passed in an array of cat and you're only storing cat-like things, then I'll JIT a test that it's an array of cat. You told me it's an array of animal. I'll test for array of cat. I'll sharpen it to array of cat right now, and then all the cat-like stores optimize away. But if you occasionally pass me in an array of dog, when I've tested for an array of cat, I'll stop or an array of animal, and I've tested for array of cat, I'll stop and blow it out and re-JIT the hard way.
Yeah, so in our IR, we have similar. So Java, give me a second to load my memory, but Java has a instance of opcode.
Yeah,
and
basically. Yeah.
And a cast.
Yeah. Stupidly, there are 3 opcodes that do this test. There's instance of, there's cast, which asserts, throws an exception if you fail, and then there's array store, which includes the test and throws if it fails.
Right. But kind of hard coded.
It's just, yes, baked into the bytecode. Yeah. But when the JIT spews them out, that's identical test code and identical optimizations done on them all.
So what we have is just 2 ops. One is a type assert, and another is a type test.
Yeah.
So the one produces a Boolean, the other produces an exception.
Which
the other raises.
Right. Yeah. Which what instance of can check has basically.
Right. And then with the IR, with the rules that we have, once that type assertion occurs, or type either one, that information flows, so that the idea was that by the time we get around to generating the code, we would be able to skip subsequent, we'd already know to get here.
Yeah.
We've already tested blank.
Okay. I'm looking for where you break out the difference between I've been typed as an array of high-level generic animal, and I'm only ever passed array of cats, and I'm doing cat-like things, versus, and that's all that ever happens, versus the case where after a while of doing cat-like things, somebody hands me an array of animal and stores a dog into it. And then where do you optimize the cat into cats correctly while denying the dog, but when the array of animal comes along, dog's okay?
That was a lot of questions.
That was one complicated scenario. I'm looking for a phase shift in behavior.
So going back to what Yorick was saying, so when we pass an array of cat, the idea is that we would generate that fat pointer for an array of animal to the same struct.
That pointer thing. Yes.
Right. But a slightly different V table. And the reason is because if we pass an array of cat into array of cat, we don't want any extra checks. But when we pass an array of cat into array of animal, we have to basically make sure that those checks occur.
And you're getting them by having your array store being a V call, being virtual. Conceptually virtual, right? And then presumably,
in fact, everything, we don't have fields, so literally everything is virtual. So,
yeah, I just checked what a TypeScript does in this regard, because they have a fairly complex type system, but they are not. Their type system is not sound. They basically, if you have a function that takes an array of animals and the input is an array of cats, you can push a dog in it. Like it won't blow up, as in at compile time.
Yeah, right.
So now I basically have an array of 2 cats and a dog.
Yeah. Declared as an array of cat. Yeah, fine.
Yeah, and that's I think in TypeScript they can probably cheat because they do have union types. Let me see if. No, it's still typed as an array of cats. I think maybe it's smart enough to say, oh, it's actually an array of cats or dogs.
What this means is that the JavaScript runtime eventually gets to make a cat-like call on a dog.
Yeah.
And you get the famous,
Should work fine. It's JavaScript.
yeah, you get the famous none is not a function error.
Right.
Whatever the hell the thing is. Yeah.
It's
So-
just different degrees of messed up.
If
Not
I were
so
in-
much it works.
If I were
They
in
also have
university
the-
at this point, I'd be doing a proof that Perl is completely transcribable into JavaScript and vice versa. It's the first two languages that have no loss in translation. And that, by the way, was not a compliment for either.
Yes. It's like no loss in translation means it sucks in both directions. And the bijection back
Sucks and blows, depending on
Right.
the point of view.
But one of the problems JavaScript has is that you can't tell whether something is an array of pointer to object or an array of object. Like that is entirely the runtime's business. The developers don't get to know that.
I think that's a
I
good
feel
thing.
like if you want to be able to control performance in your language, you want to give your developers the ability to distinguish this is an array of users versus this is an array of pointers to users.
I think both answers are reasonable. In other words, the C++ answer is, the developer has to spell it out exactly, right? And what Hotspot showed us is sometimes, where sometimes is 99% of the time, the computer will have more information when it's running than a developer does, even if they do profiling. And so, given enough time and memory, which are the two things that Hotspot uses a lot of, given enough time and memory, the computer can make a better choice for optimization. So for long running or repeatedly running or whatever, you're going to win. You're always going to win on a dynamically optimized profile-driven optimization.
I'll claim that the memory consumption has nothing to do with the JIT. It's the coding style encouraged by Java developers to save memory, but has nothing to do with JIT.
When your cost of allocation goes to zero, everything gets allocated.
The mental model is the cost of allocation goes zero. The actual cost is much higher than zero and not measured in any convenient way, but it's actually quite high.
Kirk Pepperdine would be glad to jump in at this point.
Oh, I fall over people writing code where they've run out of memory bandwidth and don't know it all the time. That's fine. Never mind. Okay. But yes, the apparent cost of allocation is zero, so people allocate. The actual cost is much higher because of.
Is it a real running out of memory bandwidth, or is it just I'm spending all of my time pointing,
it's real.
chasing pointers, so
Exactly.
I'm indirecting all the time.
Exactly. And that is why you're out of memory bandwidth. And because you're out of memory bandwidth, all the pointer chasing is expensive. Those two go hand in hand. Every time you're out of cache, you go to memory. If you're out of memory bandwidth, you're waiting for some other thing that's memory's busy serving. So all loads through those pointer chases are all slow because you're out of cache for having too many pointers and out of memory bandwidth to go get from memory. So the trick here is to not allocate wherever possible. And both you don't pay the cost for the secret hidden cost for allocation and the secret cost for indirection. The allocation cost is that everything you allocate is guaranteed never to have been in your caches since the start of the last GC cycle. So therefore, it is 100% cache miss. And when you fill up your internal high level, L1, L2 caches, because you're allocating furiously, the things it has to throw out are typically things that you've allocated not too long ago, but are now dead. So they have to be written out because the hardware doesn't understand that they're dead. So the hardware pays to read in an object whose lifetime is very short. You wait for it to come in. He fiddles to fill it. You use it a little while, and then it sits in his cache for a little while, and then he writes it out. And your memory bandwidth is churning through new objects coming in and going away. And I do this on a course where I show people just walking through a couple of gigs of log files where I get a 5x speed up by getting rid of allocation. And it's like dumbest code, single threaded, obvious for file, not in, read line, write line, read line and do math. No write lines at all. Read line, do math.
Here's the other question though.
5x speed up for not
how often is it not fast or efficient enough? And so, working at H2O, everything was not fast enough. Everything was not efficient enough because each incremental advance you got
Yeah.
was huge, right? So like, but that's,
No, you're right.
I worked on those apps too, right? So it's
Yeah,
like, I know that
there's a
custom, right?
convenience to garbage collection that's really powerful. So,
Right, because it means that there are more than 20 people in the world now who can write programs. Because when I was a kid, there were about 20 people that could write a program. The rest of them were employed doing it, and they sucked, and they built crap that crashed.
People wrote C programs by there were 1 million people writing C programs, and that sucked, and they crashed.
It wasn't 1 million. It was, but there weren't many who could build a working program.
No, there were millions of C programmers. People jumped on Java.
I understand that there are millions of C programmers, but there were 123 apps for the Apple II, and that was it, because there were only 70 programmers who could write a working program, and they did, and a couple of them wrote two. I'm just making up a number, but
yeah, right. But that's the difference between Apple II and C as it came through later. Yeah, mostly we're doing machine code on Apple II.
My point is,
yeah,
that regardless of how many developers there weren't many developers writing working code.
I will fundamentally disagree. I'll claim that Java let people write code a lot faster. So that was, and garbage collection was a big part of that. But there were lots and lots of folks writing C code, and it took a while to get the bugs out, and that's why you switched to Java. And then, the upside was GC was convenient and got rid of a huge class of bugs. Downside
I'll give you an example. So the company I worked for before I went into developer tools, so back in 1943, they built the same application 3 times, actually 4 times. Once on a mainframe. So they had a mainframe code base. They had a mainframe/mini code base. They had a C code base, C++ code base. I think it was mostly C. They had a 4GL code base and then a GUI 4GL code base. So they had kind of DOS 4GL and in Windows 4GL. And out of those 4, the mainframe one worked, right? So that built in the 1960s or whatever, and that's where they had all the revenue from. They spent 30 years building a version in C, never shipped it because it never worked. Hundreds of developers for 30 years, billions of lines of code. I don't know, I'm making up numbers. And then, so in other words, there's always people out there writing stuff, but most of it never sees the light of day.
I'd claim that the million C developers out there now are writing code that's seeing the light of day at somewhere because no one paid their salaries but wasn't actually working. I'm not claiming they shouldn't be doing a different language, or they should.
I'm not going to say where I worked previously to my current job, but I would guess that 98% of the development effort was thrown away.
And I've certainly seen a lot of big second system projects get thrown away. I'll certainly echo that one.
Seems like the point is just ergonomics really do matter. There's a reason there are a lot fewer developers who are writing C than writing Excel.
Oh,
right.
Excel. Geez. Yeah, fine.
But the point is, in Excel, in 5 minutes, I can build something that would take me, a year to do in C. Again, I'm exaggerating for
no, but there's the truth there. I'm claiming a difference in order of magnitude, not in fundamentals. Lots of C developers producing lots of code that's seeing the light of day. On the other hand, lots of Java developers as well, because it's a hell of a lot easier.
Well, and when they mess up, it's a lot less disastrous.
Well, that's the reason it's easier, is because people mess up all the time, but your bugs get caught quicker if you've got a managed runtime. No, when I talk about no GCing, I'm saying there are times and places where there is interesting performance to be had by changing your coding style.
Yeah.
When I wrote H2O, I did plenty of places where I leaned on the GC for complicated shit that wasn't in the hot path. And when wow, we're getting attacked by military jets here. Fine. It's the air base nearby. Moffett Field's been shut down for 20 years. But occasionally we get flyovers of really cool things. Fine.
Isn't Moffett used regularly?
Yes, it's been closed as a military air base for 20 years, and it's used regularly. So yes.
Oh, as a military air base, got it.
Yes, and P3 Orion sub-hunters go in and out of it every day. They're not too loud, so they're fine. But we get, I don't know, I'm not a military jet guy, but a modern fighter jet, which is louder than hell, and they'll make low banking turns over my house once a month. And if you get outside quick and look, you can see, you know, I don't know what the hell, not an F4 Phantom, something more modern, come whipping in. He's probably still half a mile in the air, but 45-degree slant, hard coming down fast, and, you know, doing a touch and go at the Moffett field.
Quite often those will be T-38s.
Oh, could be. I mean, I don't know.
Those are the trainers that they keep their.
Oh no,
so they keep their hours up.
I've seen the trainers. These are not trainers. I've seen the trainers come by too, but these are I
Probably
again. Now I gotta take another look.
Oh my God, he was not joking.
That is loud. Holy hell.
And at a 45-degree slant, like, you know, pivoting 45, going into the airbase. Maybe it was a trainer. I don't know. Fine.
So with all the mentions of fat pointer so far, is it fair of me to think of that as just an object pointer is one pointer to the instances data encode, and one is pointer is to the classes data encode?
Pretty much.
Yeah.
That's fat pointer is kind of a generic term that means not just a regular pointer, but more stuff stuck in there.
Yeah.
So sometimes a fat pointer can be used to box a value in the space that normally you pass a pointer, and then you swizzle it in a way that you can tell it's a value, not a pointer. But the term doesn't have a very precise definition. So different languages that talk about fat pointers, and each one will have their own exact meaning for it. But if you lock in too hard on what it means in one language and go to a different language, nothing will make sense. So.
Yeah. So what I hear York talking about, and what Cameron uses, I think, internally, is fat in the sense that it's two values, but that also doesn't fit in one 64-bit pointer. So you have to carry two things around at the hardware level, and that doubles the size. And if it's only done in registers, it's not too bad. And if you're storing it in memory, then the size stacks, but people don't necessarily do that. And then, let me kill my phone here.
I have not heard that ringtone for a very long time.
So the Azul hardware would carry the class ID bits in a pointer, which you could argue was a version of a fat pointer where the other half of the pointer was highly compressed pointer value. Split the difference, the 64 bits were split between address space and class space. So you could change the class of an object by twiddling the pointer bits without going past to a second word.
Yeah, that's what I was gonna say, sort of like I think the fact that it doesn't fit in 64 bits is not that important, because you can have 32 bits pointers for your language if you're okay with, you know, limiting the address space, and then fit those two 32 bits in a single 64 bits pointer. For me, it's just much more like, oh, it's just a pair of data and vtable. That's it.
Pair of data and vtable. Yeah, the better way to think about it.
And I'm still kind of thinking like this hashing approach looked interesting, but it seems you basically need inline caching for that.
You can do without the inline cache, but I claim the inline cache isn't that much more, and it will be interestingly more performant because it hits.
No, that's true. It's more like, okay, we can do that sort of on one side, and the other side is we do, let's say, fat pointers. But then I think two main problems is, one, you start have to generate all these vtables, you know, for every interface one, for every class, And
I'm not sure you might generate vtables. One per interface, one per class is like tiny, and
Right.
don't care.
Those are small numbers, so.
Yeah.
yeah, so that's the limit, assuming that, of course, in the implementation of those interfaces, the methods are sort of stored. Hold on, am I saying this correctly?
So what happens if I'm creating lambdas in a loop? I assume that doesn't create an infinite number of anonymous, but still having a vtable functions.
Right. The lambdas themselves are all the same class.
Well, and it only in languages that don't have functions. So in Java, they're classes.
Yeah, so that's my case. Like my lambdas and closures right now and methods, they're all just an instance of the type called block, and it doesn't really define anything useful on its own, other than some reflection related stuff. I am planning on turning lambdas into just functions.
Yeah,
the
where you
point.
can generate stuff on the fly that's not expected by the compiler is when you have reflection capability on binding, for example. So, give me some function or method. I'll arbitrarily bind some collection of some subset of the parameters. So maybe it's currying, I do one, then another, and so on. So each of those partial bindings produces a new type. So in theory, that could explode.
Yeah, it won't explode very far. I just think you're not going exponential, so I wouldn't really.
No, but so what I'm currently kind of leaning towards with all this info is to perhaps go down the route of tab pointers, partially because the benefit of making new types more efficient is quite compelling. Because in my language, I use option types. They are basically new types, and through this, you wouldn't need this extra allocation for the surrounding option structure. And then I'm thinking to, I don't remember if this is covariant or contravariant. I always mix the two up. But basically make it so that if you have an array of cats, you can't directly pass it to an array of animals. Like you have to explicitly cast all cats first to animals. I checked Kotlin. They do that too. So they seem to have gotten that right. Not sure what Scala does there. The only case where I can see that being annoying is that if you have an array literal, for example, that you pass directly to a argument. So you have an array, a literal array of cats, and you pass that to a function argument that expects an array of animals. You'd have to ideally extend the type inference so that it says, oh, this is not an array of cats, it's actually an array of animals. So that way you don't have to pass like a literal array of new cat as animal, new cat as animal, etc.
Read-only array, an immutable array. As soon as it's mutable and you're passing it to a function that mutates, you're in trouble, right?
Yeah, and that's currently a problem because I don't distinguish immutability.
So you said array literal, but what you meant by array literal was an immutable array.
I mean, if
you meant literal, like,
yeah,
spelled out so it was in the AST itself.
But as soon as it's immutable, as soon as it's mutable, and you pass it the cat array to the array of the animal code happily stores a dog in it, and you're in trouble.
Oh, yeah.
Right? You have a pointer to the cat array known by somebody who knows it's a cat array. You pass it off to an array that takes animal, a dog.
That's always a problem, no matter what. If you support immutability, you have to check that something's not immutable.
Array store check.
Store into it.
Yes, the array store check. Well, that's what I was trying to hear him say, because the other option would be you upcast everyone to animals, or you copy the array and replace it with an array of animal who happens to be only full of cats at the moment, but now it's truly an array of animal. But then you can't pass it to somebody who only expects an array of cat.
Not without another expensive check.
then a check on every element, because the array used to hold only cats, but somebody started dog into it, and now you have to deal with that. Yeah.
It's, I'd also, kind of two suggestions, York. One is don't pre-optimize it. Certainly think through, like there's nothing wrong with thinking through the optimizations, but get it working slow first.
If at all. Yeah. Especially if
so,
you're toying with your language feature, man.
Right, because you're still changing stuff. So you're still going to learn stuff. And if your shopping list gets bigger, it'll undo all your optimizations.
Yeah.
So don't optimize unless you enjoy it, in which case, seriously, like by all means, knock yourself out. But
it's worth mentioning there, like I'm not doing this to make it super fast now. It's more that for the last 5 years or so, I've been going sort of back and forth of these things where I implement it. You go down a path, find it doesn't work, fix it, etc. So now kind of reaching a point like, okay, I'm redoing my memory layout. Probably gonna ditch the garbage collector in favor of move semantics. And as part of that, I have to figure out how are we gonna look up methods. So I want to make sure I don't have to redo this, 12 months from now. And that's sort of why I'm kind of weighing off like, okay, we have fat pointers on one end, we have basically hashing on the other hand. And so I mentioned performance, it's more like in the future, if I want to make it fast, ideally I don't have to spend like months redoing things. It's more like, clean a few things up here and there.
Yeah, you definitely should design it for the optimizations, but you don't necessarily have to implement them all from day one. So you need to be able to see the path to the in other words, keep your contracts tight enough that they're not the main thing that prevents you from optimizing later is when your contracts aren't tight. So that, there's some random contract that says, I can ask any Java object what its internal hash code is, and it'll give me a number. And I can synchronize on it. Like, these are tiny little things that they thought were free in 1995. Because they'd written it in C, and it's like, well, here it is. It's this address in memory. Let's use the address in memory as this internal hash code. And then 5 years later, Cliff couldn't make it fast because of it.
Yeah, it wasn't me at that point. No one could make it fast. The hash code sucked because garbage collectors couldn't move code. But who was moving object code? Couldn't move objects. Who's moving objects? Well,
so you keep your contracts minimal. That is, you don't allow for accidental functionality because there's nothing free. There's something that you think is free right now will bite you so hard later, and you're like, fuck, that's what he meant. The other thing I would say is, don't start necessarily with the array of cat and dog and animal examples. Start with just cat, dog, and animal. Like, forget the container types for a second.
Yeah.
How are you going to handle it when you have food that takes an animal and you pass a cat or dog, or food that takes a cat and you pass start with the kind of simple things and work back from there, because you may start to see like why the fat pointer is beneficial for your particular design or not, right? So start with a simpler example and then expand it. So what I was going to say, we've struggled with a lot of the same questions over. I hope that most of the struggles are years behind us now, but we have a much more complicated issue with what we call a call chain, because in C++, if I'm writing a C++ compiler, for an object, I only have to know the first pointer, because the first pointer goes to a function that has hard coded the second pointer. So each function knows it's super. Right. So like all of the only virtual call is the call into this in the first case. I was thinking pure virtual C++ abstract class with the equals 0 nonsense. So, but once you're into a method chain, once you're into a function, like everything is non-virtual. In our case, it's almost like shuffling a deck of cards, because we have things like mixins, for example. So in one case, the super from foo might go to here. And in another case, because of a mixin, there may be another function inserted between those. So we don't have just the vtable challenge. We actually have this chaining challenge as well. right? And because I haven't spent a lot of time in the last 25 years on assembly timings, you know, like I know that there are severe penalties in x86 for indirection to functions and indirection to both jumps and function calls by values. So, you know, I'm talking about Cliff.
I'm writing out some Julia code that I see out of LLVM every time I look at this. Some guys, this startup I'm helping doing their this. So
Right.
they are JIT'ing separate independent chunks of code. And when one chunk calls another chunk, they load the address and call quick on it. That's like 20 to 30 clocks, as opposed to a half if they did the other version, which would have been this. Right, that's like a half a clock.
Yeah, that's the type of thing I'm talking about.
Yeah. So as soon as you did a table indirection to a register, you're 20 to 40 times slower than not.
And the other shocking one, I'm sure Matt has the link, is the switch optimizations, because I don't know what it is, but I have a fetish for switch statements. And it turns out that the cascading if is
no, Matt, it can't, because they're compiled at different times. The guy who contains the move absolute call quick is compiled first before he has the target for some function, which is compiled second, and vice versa. Right. Hotspot fixes this by code patching, by self-modifying code.
Right.
And they're exactly because it's like 20 or 30 clocks.
Right, but what if it's dynamics every time it's a different one? Right?
Yeah, right.
And that's what I was saying about switch, because you don't want to have, if you only have 5 different sum functions, then you literally want to say if.
Yes.
If.
Yeah.
Because it ends up actually, well, first of all, you don't ever have to leave the page you're on.
Yeah. Polymorphic inline cache is basically doing that. Yeah. So an inline cache does it for one in the code. Exactly, it does. If you're this, call the hardwired sum function.
So the other thing that we chose design-wise is our function chains are perfect columns, meaning there's no variance in type through the chain. And what that means is that if I have foo that takes animal and I override it on a different plane of abstractness with a foo that takes cat, say, so I narrow it, or I could whatever, pick one.
Yeah.
Widening, narrowing, something. Those actually are 2 different functions.
Yeah.
And what we do when we generate what's called a type info, which is basically a 2-dimensional V table. So it has all the virtual chains through all the levels. So we resolve all that in what's called a type info. When we do that, the column for the foo animal gets a special cap. It's called a cap on it. And the cap redirects to the new column that replaces it. So that way, someone who has a V table, say an index in a V table for this function, it hits the cap. The cap redirects almost like an invoke non-virtual in Java to the no, actually, I guess it's a invoke virtual. That's right. Sorry, that's an invoke virtual. Then it goes down this one, and the last on this chain is a super under the cap. So literally, instead of doing this, it moves it side by side. So we have the 2. So they have, I don't know how to say it, specific identities for those signatures. And then the old one gets capped, so nothing else can then override that. And the other one replaces it. And the reason it's even more complex than I'm saying, because you can actually have conditions where you have 2 different methods that override one method, and things like that because of things like covariance and contravariance. So yeah, I could. It's not gonna fit in today's conversation.
But so you need to get a little audio visual aid here. a slide dump picture slash kind of thing. I do really great online presentations on stage because I spent the week beforehand tuning up the slides to do the clean, nice. Yeah, so it looks really awesome on stage, but there's a lot of legwork. Doing them on the fly in these conversations often comes across way more stumbling for me too. I mean, it's just like hard to get.
But that was a long way, York, of saying like all of that was designed because at the end of the day, we want to be able to produce code that looks like it was written in C++.
Yeah.
In other words, +4 gets me the function I want to call. I call it. There may be indirection going on behind the scenes, but that +4 is hard coded somewhere, and I don't want to have to. So that's kind of a
+4 is what you're saying. Some point.
Yeah, you want everything to devolve to like what Cliff was saying, call to a call, or to a one level of indirection with some fixed offset into a view table.
Yeah, right. I'm claiming try hard to not have any indirection, but if you have to have indirection, just be prepared for it to be bad. So try to make it not common. Hotspot could do too low. A virtual call was not optimized by any strategy. Like CHA didn't get it, class hierarchy didn't get it. Inline cache was failing. It could be done in 2 loads and a call, and instead it's done in 3 loads and a call because there's 1 layer of indirection extra thrown in somewhere. So you get a move, jump register, and each move cannot start until the prior one gets you a thing back. So each one's a full time, which is like 3 clocks or 4 clocks now on an x86. Assuming it all hits in your L1 cache, which your object header is 50-50, whether you've seen this object before or not. If it's the first time you're seeing an object in a while, it won't be in your cache. So you'll be 10, 12 clocks getting to the call, which will be 30 more. And if you have a static call, it's half a clock. So that's the desire to arrange it that it can most of the time, boil down. In the case of Julia having this version versus the slow versus the fast version, I think their problem is that LLVM was JIT'ing code, but there's no matching runtime that will do the patching, instruction patching on the fly to allow for the faster version.
I assume that's only if you ahead of time compiled the code.
No, these folks are doing a database. They're compiling every query. A query shows up, they process the SQL level, a query optimize a while, and they come up with a pile of Julia code to execute the query over the data set. They hand that off to the compiler. So that code is not ahead of time in any way. But even where they have ahead of time code, they're getting these kinds of function calls all over the place. So I am unclear what's going on with Julia, that's happening. Julia will inline, if it's statically known, he inlines aggressively, and that's fine. And he does a reasonable job of allocation and all that kind of stuff. But there are tons of places I see where I would have thought he could have said a static call, and you get this dynamic thing all over the map, and this showing up in hot inner loops left and right. Which, yeah, turns into, well, they have some order of the magnitude of performance. So leaving on the table, this is only one of them, but there are plenty floating around. So I'm frustrated with Julia right now for having weirdly pothole performance. It's really good if you look like Fortran code, and if you're writing systems code, it can 50-50, it did okay, and 50-50, it just fell off a cliff.
So isn't Julia the one that has the multiple dispatch?
Yeah. So if you fail to get your types all statically known to the compiler, you get a horrific performance hit. And it's very mysterious as soon as you get complicated as to whether or not you got them boiled down. Like you always have these nice generic types everywhere. and then you added concrete types here, and you added some concrete types there, and after a while you think you've got concrete everywhere, but the code's being hacked on by 20 people, and it's gotten kind of big and complicated, and suddenly, no, it's a generic type at the bottom, and so there's a dynamic dispatch, and like, oop, okay, 10x performance slowdown, what? And you get a couple of those that haven't been cleaned out in 6 months or a year, and people don't know what good performance is. They know it's wrong, they don't know why it's wrong, or when it went wrong, and how it went wrong. Big mess. So trying to sort out a coding style in Julia that gives you reliable performance.
Is there a way in Julia to put an assert on some function and say like, no, this thing actually needs to be concrete?
The issue is, yeah, I think so. I think you have to have I think you can ask the question, but it gets boiled down always to something. And then the caller to the callee has the dispatch call site going painful. Yeah, okay, no, maybe I don't know. I don't know. You can ask like, what is the types, lowered types, but you're lowering it in a lot of contexts. And you've passed partially lowered things through layers, which are adding types as they go through the layers, and it gets lower each time. And then they're handed off to all these call sites. And I'm not clear if I can ask for the lowered types. Like I know we have tried to ask for lowered types in some places and failed to get Julia to tell us the lower type. Like if we're JIT'ing code that's in a quoted block of a quoted block kind of thing, and he's lowering types some and quoting it and lowering types and quoting it, I can't get the bottomed out type conveniently. So in a couple of these cases, I've had them pull everything out of their harnesses of this making code for that, making that, and write little tiny use cases. And suddenly we see, oh, in fact, it didn't get lowered here, but this was a giant cut and paste into a custom thing in order to discover this fact. So that's sort of where we're at right now. Failure to lower types frequently is one of the issues. Another one is the slow call, even when it has been lowered to statics. This is not a dynamic dispatch, by the way, not in the classic Julia sense. This is a static dispatch of something that was just JITted out of order with the different pieces. So there's a bunch of performance warts going on there. And of course, if you wrote Fortran code in Julia, it wouldn't, none of these issues would ever rise and you wouldn't care. Switch lowering improvements. Yeah, Hotspot did a lot of switch lowering. I'm staring at your switch thing because I'm changing subjects for no good reason because I'm ranting on Julia and I don't want to stop. Yep. Hotspot did this long ago. Straight comparisons, jump tables, building a tree, all kind of stuff. Histogramming. You get histogramming, you have histograms. No, okay. Fine.
Maybe I'll put some slides together for next time.
Yeah, because I'm kind of curious because I only kind of half got what you were trying to say there. And alternative dispatch logic rules or whatever are all like fun, fair game. Why did we know? Why are we doing virtual calls? Okay, because they can be done kind of sort of efficiently. Then everyone does an interface call and kind of sort of it sucks. And so now, what's an alternative plan that makes life better for interface calls?
I like Yorick's approach in general, which is, assume everything is virtual via interface and optimize for that case. Start with that as your base.
Hotspot started with the base and everything was a classic C++ virtual call and optimized from there and did a good job. But the interface calls, never got.
Well, not really good for the common case of one interface, one class, and the
yeah. Well, but
it optimizes really well for that.
Even the case of a bushy but not interface, a bushy tree, and it's a classic virtual call, you still got sort of the best you're going to get, which was a couple loads and a jump register. So, but the interfaces were always, I have a loop whose size varies according to.
So the jump register is the call queue.
Yeah. I think the best you're going to get is the load jump register for a classic interface on a bush. If I have as you're saying, yes, we've well optimized the case where there's a hot path The inline cache does the one, the doing something where you have a histogram of specs and you inline several hot cases, but as soon as you have 20 guys, kind of the uniform access, your best bet is some load jump register. Going from 2 to 1 is going to be hard, and adds 10% or subtracts 10% of the overhead. Like the jump register adds the 30 clocks. Maybe it's 20 now. Somebody was saying 20, but it's been 30 for a very long time, and the processors have not really gotten any more efficient there.
Well, I mean, the cost isn't all on the call or the jump itself. It also has to do with the CPU doesn't like to
the instruction fetch.
it doesn't like to optimize for that style.
Yeah, the CPU gets his iCache fetch stream reset, basically. So branch target buffer works if you have few enough targets floating around, but if everybody's doing these kinds of calls, the branch target buffer gets overwhelmed and fails. So you can't really rely on a BTB if you have bazillions, if you're doing it all the time. And now what's a better answer? And I don't have a good answer. The obvious array scan loop was, I don't know, hash table over an array scan is a better starting point, maybe helps. So I'm curious to see what your parallel vertical tables with caps looks like, and see if it has a better answer buried in there. I mean, it could be the better answer. I don't get it yet.
Well, we still haven't done the optimization for it.
Yep. You have a plan.
For every plan.
Yeah, the other part of that course is that when you do all the optimization, some of the complicated backup plans like don't matter, which was the realm Java was in for at least a decade. That the interface table linear scan was the backup plan. It was it always works, right, but no one ever cared until they did.
Right. Yeah, and the de-optimize, you de-optimize paths and so on.
Much more efficient. Yeah. The de-opt, compile it directly JIT in the code and de-opt if you're wrong was a huge win. You got rid of so many, normal cases. So you just didn't care on the backup plan, like I said, forever today. So you did. So you have to have a backup plan. You'd love to have the backup plan be efficient for when you care that it's the only plan. But you could argue that it's typically should be the backup plan. Bye, Max.
I am going to run as well.
It's probably time. All right, I would claim I'm going to do videos till I die, get them all out. So I don't have this one go too much longer. All right, anyone else have anything they want to add here? Final bits of wisdom. You wonder if we were on a Saturday. Well, that's a question of switching to a Saturday in general, as opposed to a Friday, where I was claiming I would catch people at work on a Friday was better than Saturday. They're off having a party.
Yeah, my marriage will last longer if we don't do it on Saturday.
Yeah. A lot of those things went out the window with COVID, but theory says we'll all be vaccinated here in 6 months, and we'll be back on to doing something on Saturday night. We're kind of stir crazy over here. We're ready to go do something. All right, not moving to Saturday yet. So this is it. I'm gonna call it. All right, see everybody next week. Bye.